Hello again, welcome back to a new video. In this video, we will be continuing solving the questions from chapter 4 review. We have question 40. It says, how much work is done when a tire's volume increases from 35.25 times 10 to the power of minus 3 meter cubed to 39.47 times 10 to the power of minus 3 meter cubed at a pressure of 2.55 times 10 to the power of 5 Pascal in excess of atmospheric pressure. Is work done on the gas or by the gas? Now, we have, first of all, we have initial volume. This is the initial volume. And this one is the final volume. You have pressure also, this is P. Now, work is going to be what? Work is equal to, let me just do this here. Work is equal to pressure multiplied by delta V. Pressure is equal to what? It is equal to 2.55 times 10 to the power of 5 Pascal multiplied by, just with a Pascal, yeah, times delta V is going to be final minus initial, so you have 39.47 times 10 to the power of minus 3 minus 35.25 times 10 to the power of minus 3. Work is equal to what? Is equal to 1.08 times 10 to the power of 3 joules. Is work done by the gas or on the gas? The work is done by the gas because we have a positive result, not a negative result. Or you can just basically get this from the question. Since the V final, the final volume is greater than the first one, the initial volume, then of course work is going to be done by the gas. Question 41. Helium in a toy balloon does work on its surrounding as it expands with a constant pressure of 2.52 times 10 to the power of 5 Pascal in excess of atmospheric pressure. The balloon's initial volume is 1.1 times 10 to the power of minus 4 meter cubed, and its final volume is 1.5 times 10 to the power of minus 3 meter cubed. From this information, determine the amount of work done by the gas in the helium, in the balloon. So we have again work, which is equal to pressure multiplied by delta V. Pressure is equal to 2.52 times 10 to the power of 5 Pascal times the final volume is equal to 1.5, so 1.5 times 10 to the power of minus 3. Then the initial volume is equal to 1.1 times 10 to the power of minus 4. Then multiply all of this, and work is going to be what? Work is going to be equal to 350 or 3.5 times 10 to the power of 2 joules. And of course, work is done by the gas. Absolute zero on the Rankine temperature scale is equal to 0, okay? And the scale unit is the same size as the Fahrenheit degree. So absolute 0 in Rankine is basically Fahrenheit, which is equal to minus 459, okay? So the equation for the first one is going to be TR Rankine is equal to TF plus 459. And for B, TR is going to be equal to 9 over 5 TK. Okay, this is just the equation for Rankine, which is another scale for measuring temperature. We have question 43. A rock, a 3 kilogram rock is initially at first at the top of a cliff. Assuming that the rock falls into the sea at the foot of the cliff and that its kinetic energy is transferred entirely to the water, how high is the cliff if the temperature of 1 kilogram of water is raised by 0.1 C, which is Celsius? Now, first of all, we should know that since the rock is falling, the potential energy or gravitational potential energy is going to be transferred to delta U. Yes, here it's talking about kinetic energy, but since the rock is falling, we're going to use the equation for potential energy, because gravitational potential energy is turning or converting into kinetic energy. So delta U is going to be equal to PE, and then delta U, let's just write this one here, it's easy. PE is equal to delta U, and then here we have heat, okay? So PE is going to be equal to what? It is going to be equal to Q, okay? Just to make sure, we have mass, which is 3 kilograms. This is mass. And then we have this one, which is the mass of the water. And then we have delta T, which is, this is going to be delta T, which is the temperature. We need to find what? We need to find the H. How high is the cliff? Now, we know both equations for PE, and we know equation for the heat too. P is equal to mgh, and Q is equal to Cp mass delta T. To find H, I'm going to divide this by mg and divide this side by mg2. Cancels, and then we have H, which is equal to Cp mass delta T divided by mg. Cp of water is equal to 4,186 times mass is equal to what? Mass is equal to 1 kilogram times delta T is equal to, it is equal to 0.1. Then again, mass is equal to what? Mass is equal to 3. I'm going to use the mass here, careful, of the rock, okay, that is falling. Then 3 times gravity is equal to, it is equal to 9.81. This is all equal to what? It is equal to 14, I think point something, but 14 meter, it's enough, okay? 14 meter. This is the height of the cliff. Convert the following temperatures to degrees Celsius, to degrees Fahrenheit and Kelvin. A boiling point of liquid hydrogen minus 252.87. B, the room temperature of the temperature of a room at 20.5 Celsius. So let's first change the first one, A. Let's find this, which is equal to minus, 252.87 Celsius. Let's change this to Fahrenheit and change this to Kelvin. Now, for TF, this is going to be what? 1.8 TC plus 32. This is going to be 1.8 times minus 252.87 times, plus 32. TF, calculate this, and you should get minus 423.2. This is Fahrenheit. This is A, careful. And then let's change this to TK. Okay, what is TK equal to? So TK is going to be what? Is going to be TC plus 273.15. Then this is going to be equal to what? You have minus 252.87 plus 273.15. Then TK is going to be equal to 20.28. Okay, this is A. B, let's change 20 point, I think it was 5, yes, 20.5. So 20.5 Celsius. Change this to Fahrenheit and change this to Kelvin. Then change it to Kelvin. TF is going to be 1.8 TC plus 32. Then TF is going to be what? 1.8 times 20.5 plus 32. TF is equal to what? It is equal to 68.9. Then let's change this to TK. TK is equal to what? So TK is equal to TC plus 273.15. Okay, now TK is going to be what? 20.5 plus 273.15. TK is equal to what? It is equal to 293.6. Okay, that's it. This is what? This is the two questions of question 44. Show that the temperature minus, this is minus 40 Celsius, okay, is unique in that the same numerical value on Celsius and Fahrenheit. So let's show that minus 40 Celsius is unique in Fahrenheit and degrees Celsius. So TF is going to be equal to what? This is careful Celsius. We have Celsius. Let's change this to T Fahrenheit. We will see that it's the same. Okay, TF is going to be 1.8 TC plus 32. So TF is going to be what? 1.8 minus 40 Celsius plus 32. Then if you calculate this, you get still minus 40 Fahrenheit. So if you say minus 40 Celsius, it's the same as saying minus Fahrenheit. The numerical value is still the same. Question 46. A hot water is operated by a solar panel, by a solar system. If the solar collector has an area of 6 meter squared, and the power delivered by sunlight is 550 watts per meter squared, how long will it take to increase temperature of 1 meter cubed of water from 21 Celsius to 61 Celsius? So first of all, we need this, which is really important. This is the power of the sunlight. We should multiply it by the area, and then we will get how much heat or sunlight is collected on this area, which is 6 meters squared. Then we will find time. As you know that power is equal to energy divided by time. So we need to find first energy. Let me write this. Power is equal to energy divided by time. This is the only equation that I can use to find time. So time is going to be equal to what? It is going to be equal to energy divided by P, or power. Now, if you think about it, how can I find the energy first? Okay, how can I find the energy when the only thing that I have is 550 watt per meter squared, and I have 6 meters, and I have 1 cubic meter. Let's go. Now we have, let me erase this. Yes. We have 550 watt per meter squared. This is the amount of sunlight that it is collecting. I should multiply this by what? By 6 meter squared to get what? To get the P total, okay, the power. If you multiply this, you're going to get what? You're going to get P total, which is equal to 3,300 watt, okay? Or you can say joule per second, as the equation for power is equal to energy per time. So this is joules, and this is measured in seconds, okay? This is my first given, 3,300 watts, or joule per second. Now, how can I find the energy? Now I have power, okay? As you see, I have found power, but I don't have energy. How can I find the energy? Okay, to find the energy, guys, remember that Cp, Q is equal to what? Is equal to Cp mass delta T. But you will say, I don't have the mass too. How can I find the mass? Remember, density was equal to mass divided by volume. Then mass is going to be what? Mass is going to be equal to density multiplied by volume. Now, we are dealing with what? We are dealing with a hot water. Okay, can I find the density, the mass of it using the density? So mass is going to be equal to what? 1,000, which is the mass of the water, times the volume. Do I have volume? Yes, the volume is equal to 1. So 1 meter cubed. So mass is equal to 1,000 kilogram. This is my mass. I have Cp2, Cp of water is 4,186, and I have delta T2. Okay, delta T is equal to what, guys? Delta T is final minus initial. I have from 60 to what? To 60, which is final, and 21. Now let's find Q. So Q is going to be what? is going to be 4,186 times mass, which is equal to 1,000. We just found it. And then time is final minus initial, which is 61 minus 21. Multiply all of this, and Q is going to be equal to 1.674 times 10 to the power of 8 joules. This is my energy. Okay, this is the energy that I was trying to find. Now let's find time. As you remember, time was equal to energy divided by power. Do we have power? Yes, we have power. Power is equal to 3,000. As you remember, power was equal to 3,300 joules per second. Okay, now let's find this one. Time is equal to what? Is equal to energy, which is equal to 6,744 times 10 to the power of 8 joules. Then 3,300 joules per second. Joules cancel, and you have what? You have time, which is equal to 50,700 seconds. Okay, divide this by what? Divide this by 3,600, and time is going to be what? Time is going to be equal to 14 days. Okay, this is the time, this is how long it will take to raise the temperature of water from 21 to 61 Celsius. A student drops two metallic objects into a steel container. So we first have a steel container holding 150 grams of water. Okay, this is water at 25 Celsius. One object is 253 gram cube of copper. So I have this one, copper, which is equal to mass is equal to 253 grams. You might say, why aren't you using the steel mass? I'm going to explain it in a minute. The copper is initially, so T initial for copper is equal to what? It is equal to 85 Celsius. Okay, and what else do we have? We have the other one, which is aluminum. So aluminum is at 5 Celsius. So T initial for aluminum is equal to 5 Celsius. And to the surprise of the student, the water reaches a final temperature of 25 Celsius, its initial temperature. You see, the water reaches 25 Celsius, okay, and its initial temperature. So there is no change in the temperature of the water, careful. There is no change in the temperature of the water. And where is the container? What is the container? The container is a steel container. So there's going to be no heat transfer to this container too, because temperature, the final temperature and the initial temperature are both the same. Now, what do I need here? I need Cp of aluminum, which is equal to 899. I need Cp of water, which is equal to 4,186. Now, what do I have to find? I have to find what is the mass of the aluminum. Okay, now this is going to be like this. Q lost by the aluminum is equal to Q gained by the copper. Okay, now Cp mass delta T is going to be Cp mass delta T. Now Cp of aluminum is equal to 899 times mass, which is equal to, no, we don't have it. Then delta T is going to be equal to what? It's going to be T initial minus T final, 5 minus 25, which is the final one. I forgot to write. T final is equal to 25 Celsius. And for this one is also T final is going to be equal to 25 Celsius, since both they are in water. They are both in water. So 4,186 times mass, which is equal to 253. Change this to kilogram. 253 times 10 to the power of minus 3 kilogram. And then we have 253 times 10 to the power of minus 3 kilogram times delta T is going to be what? Delta T is going to be final minus initial. Okay, so 25, which is the final one, subtracted by 85, which is the initial temperature. Now, multiply all of this and you get minus 17,980. Don't forget this mass, okay, which is equal to what? Is equal to minus 5,874.66. Okay, you have minus from both sides, so they're going to cancel each other. Subtract this by minus 17,980. Subtract this one too, divide this one too, 17,980. And then cancels. Mass is equal to what? These two cancels too, of course. Mass is going to be equal to 0.326 kilogram or 326 grams. Okay, this is the mass of the aluminum. Now we have question 48. Let me erase all of this. We have question 48. Question 48. Question 48. A 250 gram aluminum cup holds and is in thermal equilibrium with 850 gram of water at 83 Celsius. Okay, the combination of the cup and water is cooled uniformly so that the temperature decreases by 1.5 Celsius per minute. At what rate is energy being removed? So first of all, the rate is going to be like this: Q energy divided by time, okay, divided by delta T, which is going to be equal to what? Is going to be equal to is going to be equal to Q of aluminum, which is heat of aluminum, plus the Q of water. Okay, and again we have what? We have delta T, temperature. Okay, this is over temperature. And let's continue this. Delta T is going to be Q of aluminum is going to be Cp mass delta T plus Cp mass delta T of water. Divide this all by delta T, which is changing the temperature. Careful, this is time and this is changing the temperature. Now take both of these out. Okay, this is not delta T, this is delta time. Okay, this is changing the time. Now take both of these out. Okay, take this as a common between these two, and then take this out too. So this is going to be what? This Q divided by delta T is going to be equal to Cp mass plus Cp mass of water. This is aluminum, and this is water. And multiply by what? Multiply by delta T divided by delta time. Okay, changing the time. Now Cp is going to be what? Cp here for the water is going to be for the aluminum, so Q, which is the rate change, is going to be what? 899 times mass is equal to what? Mass is equal to 250 times 10 to the power of minus 3 plus Cp is what of water, 4186 times mass, which is equal to what? 850 times 10 to the power of minus 3. Okay, what is delta T? Okay, if you remember, it says 1.5 Celsius per minute. Okay, so this is going to be what? This is going to be 1.5 Celsius per minute. Okay, now calculate all of this and you should get what? You should get 5.7 times 10 to the power of 3 joule per minute. Okay, joule per minute. Okay, Celsius is going to cancel. You can divide this by seconds, and this one, divide this by 60, and Q divided by delta T is going to be equal to 95 watt. Okay, because it's going to be joule per second, or joule per second. Let's just write this one. Okay, this is question 48. We have question 49, a jar of tea is placed in sunlight until it reaches an equilibrium temperature of 32 in an attempt to cool the liquid. It has a mass of 180 gram, and let me just erase this. Okay, now 180 grams. 112 gram of ice at 0 Celsius is added. At the time at which temperature of the tea is 15 Celsius, determine the mass of the remaining in the jar. So we are trying to determine how much ice is the remaining from 112. Okay, assume that the specific heat capacity of the tea to be that of pure liquid water. Okay, so this is good information. So Q of the tea is going to be equal to what? It is going to be equal to Q of the ice plus Q of the ice. You might say, what is this? So first of all, the ice is melting down. This is going to be MLF. And then we have the ice, which is going from 32 to 15, careful, okay? Now this is going to CP mass delta T. Let's write this. So QT is going to be MLF, which is plus CP mass delta T. Now, as you see that mass here, just let me delete this, okay. As you see here, the common thing between them is mass. They both have mass. Let's take this as the common. So QT is going to be what? It's going to be mass LF plus CP delta T. And if you remember, I'm trying to find the mass of the remaining ice, okay? So divide this by what? By LF plus delta T, CP delta T, and divide this side by LF plus CP delta T. So this cancels. Mass is equal to Q of T divided by LF plus CP delta T. Okay, now this is going to be what? Again, we have Q of T, which is equal to CP mass delta T. I have mass of the T, which is equal to 180 grams, and then I have CP of water, and then I have T of water, temperature, the T final and T initial for the water too. So this is going to be 4,186 times 180 times 10 to the power of minus 3 times 32, which is the final one, minus 15, which is the initial one, divided by what? LF for the water is what? Is 3.33 times 10 to the power of 5 plus CP of the ice is 4,186. Then sorry, this is not CP of ice, this is CP of water. Then 4,186 times what? Time is 15 final minus initial, 15 minus 0. Okay, then calculate all of this, and mass is equal to 32 grams. You get 3.2 first times 10 to the power of minus 3 minus 2 kilogram. Change this to gram, this becomes 32 grams. This is the mass of the ice that is melting. But is it the final thing? No. The initial one, guys, the initial mass of the ice was 112 grams. Okay, and then 32 grams has melted. So we're going to say 112 minus 32 is going to be 80 grams. So this is what? This is the mass of the remaining ice. That is it. We have solved all the questions from chapter 4, review and assess. If you have any questions regarding any questions, please comment below. See you in the next chapter and in the next video.